Hello, this is Mathematics Tech Talk. My name is Chaitanya. I am from the section ITA and my roll number is 21951A1219 and my Tech Talk topic is estimation of the entropy and information of absolutely continuous random variables. Basic theory. Our starting point is a measurable space S, S, that is, SS is a set and SS is a sigma algebra of subsets of S. In the last section, we discussed general measures on S, S that can take positive and negative values. Special cases are positive measures, finite measures, and our favorite kind, probability measures. In particular, we studied properties of general measures, ways to construct them, and special sets positive, negative, null, and the Hahn-Jordan decomposition. The answer to the question involves two important relations on the collection of measures on S, S that are defined in terms of null sets. Recall that capital A belongs to set S is null for a measure mu on S, S if mu of B equals 0 for every B belonging to the set S with B it may belong to or may be equal to A. At the other extreme, A equals S is also a support set for mu. If AC is a null set, here are the basic definitions. Suppose that mu and V are measures on S, S. V is absolutely continuous with respect to mu. If every null set of mu is also a null set of V, we write V is very less than mu. Mu and V are mutually singular if there exists A belonging to S such that A is null, and for mu and AC is null for V, we write mu is perpendicular to V. Absolute continuity and singularity are preserved under multiplication by non-zero constants. Suppose that mu and V are measures on S, S and that A, B belonging to R such that A, B belonging to R divided by 0, then V is very much less than mu into V less than mu if and only if AV is very much less than B into mu into A into V less than B into mu. V is perpendicular to mu V is perpendicular to mu if and only if AV is perpendicular to B mu AV and which is perpendicular to B mu. Abstract. A method is proposed for estimating the entropy and mutual information of absolutely continuous random vectors and an upper bound of the main risks for the proposed estimators under strong mixing conditions is given. Introduction. Let X be a random vector with values in R to the power of m and probability density function f of x. The entropy of X is defined by h in X is equals minus of integral from Rm into f of x log of f of x dx. We shall always assume that f of x into log of f of x is integrable. The first way to estimate the entropy of a discrete random variable was proposed and analyzed by Bashharin and later by Hutcheson and Shenton. For a random variable with density, Ahmad and Lin proposed the following approach for m equals 1. Taking a random sample x1, x2 and so on till xn of x and a positive kernel k of x, f of x can be estimated by fn of x equals 1 by n into h of n summation of I equals 1 till n k of x minus xi by hn, where hn is a sequence of positive real numbers which are converging to 0. Using this, they estimate h of x by h of n equals minus 1 by n of summation from 1 to n log of f of n of x of I, and study the first and second mean consistency of h of n. However, their proof is incomplete. More precisely, they systematically use a Taylor expansion of the following form: log of z minus log of c equals z minus c by theta z plus 1 minus theta c, where theta lies between 0 and 1. But in their work, z and c are functions of n and x, and theta is a random function of n and x, so theta must be integrated and its limit studied for n tending to infinity. Another approach is due to Dmitriev and Tarasenko. They propose the following estimator: h cap of n equals minus of integral from minus kn to plus kn, where f of n is a function in x into log of f of n into x dx, where kn is an increasing sequence of positive real numbers tending to infinity. Purge studied a similar estimator where f of n is the empirical density estimator. Another interesting approach is due to Waziek, who uses his result for testing the normality of X. This approach is also used by Dude-Wicks and van der Meulen for testing the uniformity of X. Unfortunately, the method of Waziek based on order statistics is particular to the one-dimensional case and cannot be used to estimate h of x in the multidimensional case or the mutual information of two random variables. Except in Birch, there is nowhere an upper bound of the mean risk for the proposed estimators. Here, we propose an other approach based on the following well-known result. If mu is a probability measure on omega and the positive function f belongs to L to the power of mu d of mu for some q greater than 0, then 1 by r log of integral f to the power of r d mu r to 0 integral log of f of d mu. Using this, we can estimate h of x by h of n of x equals minus 1 by rn log of integration from Rm into Fn to the power of Rn plus 1 of x into dx, where Rn equals Hn to the power of gamma for some fixed positive real number gamma. Using some mixing conditions, we obtain the following result for p greater than 0 and gamma equals 1. E of Hn of x minus h of x to the power of p equals O into n to the power of minus p by 2 into Hn to the power of minus m plus 2 into p by 2 and plus h of n to the power of p. The same upper bound is obtained for the mean risks of the natural estimator. H naught of n into x equals minus of Rm Fn of x log of f of n into x dx. Continuous distribution. A continuous distribution f is continuous in the usual sense of a continuous function. One definition, usually the first one people encounter in their education, is that for each x and for any number e greater than 0, there exists a dow depending on x and e for which the values of f on the dow neighborhood of x may vary by no more than E from f of x. It is a short step from this to demonstrating that when a continuous function f is the distribution of a random variable x, then pair of capital of x equals 0 for any number x. After all, the continuity definition implies you can shrink sigma to make PR of x belonging to the range x minus dou, x plus dou as small as any e greater than 0, since 1, this probability is no less than PR of x capital of x equals x, and 2, e can be arbitrarily small. It follows that PR of capital X equals 0. The countable additivity of probability extends this result to any finite or countable set B. Absolutely continuous distributions. All distribution functions have defined positive finite measures μf determined by mu of f of the range a comma b equals f of b minus f of a. Absolute continuity is a concept of measure theory. One measure μf is absolutely continuous with respect to another measure lambda, where for every measure set E, lambda of E equals 0 implies mu of f of E equals 0. In other words, relative to lambda, there are no small measure zero sets to which mu f assigns large non-zero probability. We will be talking lambda to be the usual Lebesgue measure for which lambda of range a comma b equals b minus a is the length of an interval. The second half of the program states that the probability measure mu of b equals p of x equals b is absolutely continuous with respect to Lebesgue measure. Absolute continuity is related to differentiability. The derivative of one measure with respect to another is an intuitive concept. Take a set of measurable neighborhoods of x that shrink down to x and compare the two measures in those neighborhoods. If they always approach the same limit, no matter what sequence of neighborhoods is chosen, then that limit is the derivative. There is a technical issue. You need to constrain those neighborhoods so that they don't have pathological shapes. That can be done by requiring each neighborhood to occupy a non-eligible portion of the region in which it lies. Differentiation in this sense is precisely what the question at "what is the definition of probability on a continuous distribution" is addressing. Let's write d of lambda μf for the derivative of μf with respect to a. The relevant theorem, it's a measured theoretic version of fundamental theorem of calculus asserts μf is absolutely continuous with respect to lambda if and only if mu of f of e equals sigma of e d lambda into μf of x d lambda for every measurable set E. In other words, absolute continuity of μf with respect to lambda is equivalent to the existence of a density function d lambda of μf. We can consider a roll of a fair die and calculate the entropy of the variable. Each outcome has the same probability of 1 by 6. Therefore, it's a uniform probability distribution. We therefore would expect the average information to be the same information for a single event calculated in the previous section. Calculate the entropy of a dice roll. From the math import log tool, we have the Python program n equals 6, p equals 1.0 divided by n. Entropy equals minus sum of brackets open p to the power of log 2 of p for in range of n. Print entropy percentile dot 3 of bits percentile entropy. Running the example calculates the entropy as more than 2.5 bits, which is the same as the information for a single outcome. This makes sense as the average information is the same as the lower bound on information as all outcomes are equally likely. Thank you.